Hello everyone. Today we want to talk about the stress analysis in beams. Beams are one of the most important elements in any structures, from bridges and buildings to airplane wings and car frames. They carry loads safely and resisting bendings and shear stresses. In a stress analysis, understanding internal forces inside a beam is the first step to determining any safe and efficient structures. Internal forces like axial forces, shear forces, and bending moments tell us how a beam reacts when external loads are applied to them. In this video, we will start from the very basic, what internal forces are, how they form, and how to find shear forces and bending moments diagrams step by step. This will be the foundation of the rest of series. There will be several videos in this series moving from simplest to more complex beam analysis. If you watch them in sequence, you can learn all essential concepts of stress analysis in beams in less than 1 hour. Okay, let's start with what we mean by internal forces in beam. When a beam carries external loads, internal force develop at every cross sections to keep the beam in equilibrium. These are named as axial force. If I show you, here is axial force, for example, here axial force, or shear force that we show V. Here is shear force and bending moments. Shear force generates shear stresses, which is highest at neutral axis, and it is critical to prevent sliding or shear failures. If you remember from the strength of the material, we have tau equals VQ per IT, and maybe next videos we talk about that in details for stress analysis in beams. And for bending moment, we have the normal stress because of the bending that classified to tensile and compressive. And we show at sigma equals my per I. For example, if we have bending moments here, the be under the neutral axis, be under the tensiles, and after that, be under the pressure. Okay. This is what we use in bending stress analysis and fracture design. Axial force, whether tensile or compressive, means when outward to the cross section, considered as tensile, inward to the cross section, considered as compressive, and they cause uniform normal stress across the section. Very important for column axial forces and tension members, but not so important for beams. In beams, focus more on shear stresses and bending stresses or normal stresses because of the bending. In real structure, these effects combine understanding where maximum stresses occurs under combinations of N, V, and M, and this part is very critical and key to safe and economical design. Okay, now let's look at the external loads that create those internal forces. Beams may carry several types of loads. They start with concentrated or point load as L or P that you see here. Here you see the loading conditions, and after that, after the arrow, you see the equivalent of that. Why we say concentrated or point load? Because load applied only to one point and equivalent to same condition. For distributed load, one of them that's very common is the uniform distributed, means if you consider that it is omega or Q or something, and this length is L, the equivalent equals the area of that. Here we have the rectangle, so the area should be WL that you see as equivalent and then apply at the center of area. For example, it is this rectangle, half L left side, half L right side. The next distributed loading that is common to is the linear or triangular distributed load or linear varying load where intensity change along the beam. If you consider here is W reach to 0, this length is L, the area of the rectangle is half L times W or WL per 2 that you see is equivalent and apply to the center of this area. The center of rectangle is L per 3 at the left side, 2L per 3 at the right side. Okay, and concentrated moment, when moment or torque applied to specific point, we consider that an equivalent same. And of course, combinations of step loads, different type of loading, where load types change along the beam, that is very common and important. You see several examples of that. For example, at the top one here, we have uniform distributed load, the first one. Here is the concentrated moment that is 300 pound-feet. And here we have the concentrated load, 200 pounds. Here we have the one curve that it is not linear, triangular, not rectangular. This is completely different. We can write that is the rectangular plus one distributed loading that is curve type, curve distributed loading that you see the functions, or here we have uniform distributed load at one side, we have the concentrated. These are combinations of all of them. Okay, internal forces. Before you size or select any material, the very first step is to determine the shear force and bending moments diagrams. These diagrams tell us where the beam experiences the highest stress. So you can design for both strength and economy. What's the meaning? It means first we should find the shear force diagram. From shear force diagrams, we can find shear stresses. Then from the bending moments diagram, we can find the bending stresses. The combinations of them and finding the principal stresses, we find that in which cross section be critical means we should add any area that reinforce that part or use another material or something. So before designing the first step, we should find shear force and bending moment diagram. Whether you are designing a bridge or machine shaft or aircraft spar, you always start with internal forces, then move to stresses and deflection analysis. When we analyze a beam, we want to find force acting inside the beam that name as internal force at a specific point. For example, suppose we want find the internal force at section B. The process is this: find the support directions first. Then make an imaginary cut at B. Means we consider separate this part from other part, for example, at point B, and draw a free body diagrams for one side of the beam. Which side of the beam? Definitely we work with the side that have the minimum external forces. Why? Because writing equations of equilibrium will be easier for us. For example, for B, for this beam under this loading condition, as you see here, if you consider the left side is easier for us, okay? So we find here we have dx, dy reactions of the supports and ay. As we don't have any external force, dx is 0. The next step we find dy and ay. For example, we find ay is 5 kilonewton. Exactly before reaching to 6 kilonewton, considered B. And we have the directions that we consider that conventional directions. If we consider left side, V should be downward for being the positive. NB always should be outside of the cross section as a tensile stress for being or considered as positive directions, and MB for left side be counterclockwise for considered as positive. Then we write the equations of equilibrium or EOE. We write summations, for example, if x is 0, as we don't have any external force at x direction, so NB is 0. We write summations if y is 0, okay, 5 kilonewton upward positive, VB downward negative equals 0. So we find VB is 5 kilonewton. And we consider positive, right? When we consider positive means the direction we assumed is correct. So VB should be downward. And what about MB? We write the summations of moment around which one exactly imaginary cut at the point that we are looking to find the moment. At that point, we write summations of moment around that point. That here the point is B. Okay, VB doesn't have any space from B, so doesn't make any moment around this point. MB, you consider the directions of my thumb counterclockwise outside of the screen is positive. MB minus the moment of A, the directions of my thumb inside should be minus 5 times 3 equals 0. So MB is 15 kilonewton meter. When we find positive, means direction that I assumed here is correct and should be counterclockwise. And you see, I showed the direction here too. Okay. Internal forces, part 2. In two-dimensional beam, the internal loads at cut sections are normal or axial force that you see here, NB and B, acting perpendicular to cross-section area, shear force that you see here, VB. For left side, I told that the conventional directions should be downward for positive, for right side, upward. Bending moment for the left side, you see the counterclockwise, conventional directions for being positive, and for the right side, clockwise direction. But it's very interesting that the forces and moments on the left and right side of the card are equal and opposite. So they cancel out each other. Why? Because they are internal forces. And this ensures equilibrium when the beam is reconnected. Okay, let's summarize the steps for finding the shear forces and bending moments at the specific point, or for diagram curving for shear force and bending moments. Okay, the first step, take an imaginary cut where you need to find internal forces. Second, find support reaction using a free body diagrams of the entire beam. It depends. If it is two-dimensional, we write 3 equations of equilibrium: summation of x0, summation of y0, and summation mc0. If it is three-dimensional, we need 6 equations, EOE. Okay, after that, consider the draw a free body diagram of one side of the cut or imaginary cut. Which side? Definitely should be smart for choosing the part that have the minimum external forces, or so simple, not complex, because easier working with them. And then write the free body diagram for that parts and find the shear force, axial force, and bending moment. Okay. Example. Now let's go through an example. We are given a beam with a certain loadings. You see that it is a uniform distributed loads between point, I name this one D, up to A, okay? And we want to find the internal forces at point C. First, plan a cut at point C. We can consider 2 imaginary cuts, left side or right side. Definitely by look at that without finding the support reactions, it is so clear that right side is easier for us. Why? Because we don't have any external forces at right side except the support reactions at point B. So we considered point B. Then Find the support reactions, means at point A and point B. Okay, at B, we have Bx, By. Yeah. At A, we have Ay. As we don't have any external force at x direction, summation of x0 reach us to bx0. Summation's moment around point, for example, A0. The equivalent of trickle point should substitute by equivalent of that. It is rectangular. What is the area of the rectangle? This area. 3 times 6 should be 18 and apply at the center of the area, at the center of this rectangle. Okay, summation's moment. Bx gets 0 and doesn't have any moment. By, the moment of By, if you see my directions of my thumb, should be inside, should be minus By. The distance from this up to this is 9, okay? For 18, 18 times 3, we find By equals 6 kilopound. And it is positive, means direction that we assume is correct. It should be downward. Another summations Fy0. 18 minus downward, Ay upward, and By downward equals 0. So we find Ay 24 kilopound upward, and it is another reactions of support that we need that. Okay, I thought that the right side is easier for us. For the right side, if you remember, as convention direction, we see we can consider it upward for being the positive, okay? And MC, we can consider the clockwise directions. Okay, we write that NC is 0. Why? Because we don't have any external force, so definitely we don't have axial force. We find VC is minus 6 kilopound. When it is minus, means opposite directions that we consider that here, okay? And for MC, we find minus again, so moment should be opposite directions of that. It is clockwise, it should be counterclockwise. Okay. Here is a key relationship you will use in every beam problem. The rate of the change of moments means shear is derivative of the moment. Yeah. Or from this reach to this equation, dm is v dx. Integral of dm is mb minus ma is integral of v dx. What's the meaning? Means the change of the moment from A to B is the equal. Integral means the area. Area of the shear force diagram between XA and XB. Here, we have dv per dx equals q. We know that v is dm per dx. If you substitute the second derivative of the moment equals q, yeah? So we write that the difference between the shear forces equals the integral or the area under the distributed load. So if we have the distributed load curve, integral of that reach us to shear diagram. The integral of that reach us to moment diagram that we talk about that in details in next videos, how we find that by using singularity, finding the distributed load and vice versa. Okay, thank you so much for watching this lesson on internal forces in beam. If you enjoy it, please like a comment and subscribe to my channel, MechTalks 2025, for the next videos in this series. In less than 1 hour, you can learn everything that you need about stress analysis of beam using the shear force and bending moment diagram to identify critical points safely and accurately. The next part explaining the relationship between load, shear force, and bending moment, and then we will solve several problems about the concentrated forces.